Hi, I'm Zor. Welcome to Unizor Education. Today I would like to present you some kind of example of how Euler-Lagrange equation is used in one particular case. Now, before we were talking about like purely, I would say, artificial example of a pendulum, and it gave us very nice results, especially because we have replaced constrained Cartesian coordinates with unconstrained generalized ones. Now today is more practical, so to speak, example. It's about gravitation field and the planets moving around. We did address this particular issue in previous lectures before we introduced Lagrangian. So we were talking about Kepler's laws of planetary movements. The first, the second, and the third law. I do suggest you actually to maybe read again the material about these lectures. So all these lectures are presented on Unizor.com. It's part of the course called Physics Plus. And yes, there is a chapter or part of the course which is called Kepler's law. And right now we are in the chapter or a part which is called Lagrangian. So I'm going to present you Lagrangian's Lagrangian mechanics applied to gravitation to basically derive the Kepler's law differently and easier. I would say significantly easier, because we are not moving vectors around. It's much more simpler with energy. So we will derive certain differential equations, and from which we will derive the laws of planetary movements. So that's the plan for today. And by the way, I do suggest you to use Unizor.com as the source. I mean, if you found this lecture somewhere on, let's say, YouTube, it's just lecture by itself. On the website, Unizor.com, it's part of the course. And I do suggest you basically to take the whole course. Everything is totally free. There are no advertisements. Sign in is not necessary. Everything is basically free for all and all for free. All right, back to business. Well, I will refer to certain things as known facts because I have addressed it in previous lectures, and one of those was that in the central gravitational field of the Sun, let's say, the planet is moving within the plane. So the whole orbit is not like in three-dimensional, it's all flat. So I'll use it as given, basically. It was proven in previous lectures when we were talking about centralized gravitational field, any centralized field actually. All right, so if this is a plane, I'm going to use generalized coordinates and Euler-Lagrange equation. Generalized coordinates will be just plain polar coordinates. So we have a plane where the movement actually is occurring. Let's say it's a sun and a planet, okay, or it doesn't really matter. Sun is a central gravitational force. So I will use r of t and theta of t as polar coordinates. Now the central source of gravitation, sun, let's say, will be the origin of polar coordinates, and some kind of a line on the plane of movement will be the basis line for starting the polar angle. Okay, now to use Euler-Lagrange equations, we need to construct Lagrangian, which is difference between kinetic and potential energy. Now kinetic energy, this is 1/2 m v squared. V is basically magnitude of velocity vector. Now if you will represent it as projection on radial square plus projection on angular square, it will be speed projected on the radial will be first derivative of the radius square, and speed projected on angular component would be r times theta square. Again, I did address it many times when we were talking about movement in the polar coordinates. So I'm just taking it as given. Again, previous lectures addressed this many times. So we have the expression for kinetic energy. Now, potential energy. Now, potential energy in the gravitational field, again, we did consider it many times before, so I'll just take it as given. It's a gravitational constant times mass of source of gravitation, let's say sun, and times mass of this particular object, planet, which is moving, divided by distance between them. So the force is inversely proportional to distance square, force of gravitation. Potential is inversely proportional to radius. Okay. Now we basically have Lagrangian, and what kind of equation we really have to do? Well, in this case we have two different generalized coordinates, so it's two different equations. Again, this is just regular form of one and another by theta. Okay, so we have a system of two differential equations, two different functions of time. R is a function of time and theta is a function of time. Well, basically all we have to do is just, do this type of partial derivative, etc., and we will get to the point. All right, so let's do it one by one. So this is kinetic energy, this is the potential energy, and the difference between them is Lagrangian. Okay, so let's do it by R first. So dl by dr. Okay, so what is it? Now this is independent of R, so this is only dependent. So if we will differentiate it by R, R is square actually, so 1/2 and m will stay, and theta prime square will stay, and the only thing which will be really differentiating is r square. The 2 will cancel the 2, so we will have m r theta prime square. That's from the kinetic energy by R. All right? I'm checking myself. Okay. Now this should be differentiated by R. It will be t minus u, so that would be plus. And when we will differentiate 1 over r, it will be minus 1 over r squared, so it's minus g. So this is left part of the first equation. Okay, what is the right part? Well, the right part is differentiation by partial differentiation by r prime. Now the kinetic energy T has it, potential doesn't even have it, so all we have to do is differentiate this. This is also not related to r prime, so only by r prime, that would be mr prime. Mr prime, and after that we differentiate it by time. That would be times, it would be another derivative by time. Derivative from r prime is r double prime, so that's the second derivative of r. by time. Okay, let me just separate this. Okay. So this is my first equation. My second equation. Okay, by theta. Kinetic energy doesn't really depend on theta, and potential energy doesn't really depend on theta. So we'll have 0 on the left side. On the right side, by theta prime, again, well, potential doesn't depend on theta prime, only this one. So what it will be, r square will remain. It would be mr square and theta prime. We are differentiating, partially differentiating by theta prime. Okay, and then we have to differentiate by time again, so it's double prime here. Okay, so basically these are two differential equations for two functions, r of time and theta of time, and well, the solution is whatever we need, the generalized coordinates dependency on the time as the planet moves around the sun. Well, obviously that's not really nice to put the point here. We have to continue, because in polar coordinates it's not really r of t and theta of t. Traditionally polar coordinates is r of theta. So we somehow have to derive from this type of equation, dependency of the radius, the distance from the angle. That's how the true polar coordinates, and that's how all the orbits actually are expressed in. So let's just do a little bit differently. Well, first of all, if the second derivative is equal to 0, it means that the first derivative is actually constant, right? So from this we can have that this is equal to some kind of a constant L and have only one derivative here. Or, even differently, I will put m here and call it k. It's some kind of constant. Now, first of all, what we can do actually is we can express this theta prime as a function of r squared, put it here, and we don't have theta at all. However, we do have r double prime, second derivative of r, by time. Again, that will not help us to have the function r of theta. So we need to do some kind of tricks here. And the tricks is to convert derivative by time of r into derivative by theta, and derivative of theta by time, and derivative of theta by time. We again know how to do it from as a function of r. So from here we will have that theta prime is equal to k divided by r squared. So we will use this one, and we will use the conversion from derivative by time to conversion derivative by theta and theta by time, and theta by time we again replace with r. So this is just a little, technical kind of things. What are we actually going to use? Let me just write this down so you will see what I mean. Take any x. If you want to derive the derivative by time, you can say that this is derivative by theta times derivative of theta by time, right? Now let's do it. Prime dx d theta, theta prime. Prime is always derivative by time. So as you see, we can always use, instead of this, we can use this. And again, and theta prime would be derived from here. And that's how we get rid of the derivative by time, using derivative by theta and theta prime, which is in turn is derived from r. Okay, so this is just a little gymnastics. So let's do it this way. First, let's put r prime. What r prime is equal to? Well, r prime is, well, if x is equal to r in this particular case, so it would be dr by d theta times theta prime, and theta prime in turn can be from here, so it's dr by d theta times k r squared. Okay? Now, in turn, 1 over r squared, it reminds you, obviously, derivative from 1 over r, right? So we will have now if I want to, well, if I want to again make another r double prime, second derivative from here, it would be what? Again, we will do it by theta and then theta prime. Right, so it would be d by dt of this thing, and this thing I will convert into, okay, 1 over r derivative is 1 over r squared with a minus sign, right? So I will use this and I will put minus k derivative of 1 over r by dq. Am I right? Derivative of 1 over r over q, it would be derivative by r, which is minus 1 over r squared, which is this one with a minus, times derivative of r by q. Yes, that's what it is. That's correct. And now we would like to derive it by dt, which means again we will use it by dq first, d theta first. It's equal to minus k d2 1 over r by d theta 2 times derivative of theta by time, which in turn we can replace with this one, and that would be k over r squared. So this is the second derivative, and that's exactly what we need to do. Yes, here. That's what bothers us all the time. So basically that's it. The thing is finished. The only thing is I have to just, put everything into proper place and we will see. So let me just wipe out this thing and we will substitute everything to a proper place. So m r theta prime square, which is k square divided by r to the fourth, right? Minus g m divided by r square equals to m, and this, which is minus k d1 over r d2 over r by d theta square times k over r square. Alright, so first of all, m goes out. Let's multiply everything. Now here we will have r to the third degree. Okay. Now we can multiply everything by r square, so we'll have only r here and nothing here and nothing here. Now minus k would be k square. With a minus. Well, that's almost it. Well, let's divide it by k square. And now we have a very simple thing. Look, this is 1 over r and this is 1 over r. So let's just put 1 over r is equal to x. So what do we have? We have x, we have d2x by d theta square, go to the left, plus 1 over r, which is x, is equal to gm over k square. You see how simplified everything is now? So we did not really get function r from theta. We got expression from 1 over r for x, right? Now this is a known differential equation, second order. It was considered many times in literature and in my course as well. Obviously, second derivative of the function and the function itself, it implies trigonometry, like sine or cosine, etc. Now, general solution of this is basically a plus b cosine of theta, but we will express it differently. I mean, if you will do it really accurately, you will have a different expression. It would be, let me put it this way, it would be gm k square plus c of cosine theta minus theta 0. So we have two constants, c and theta 0, which are initial conditions, initial angle and initial proportional constants, and that's the solution in real life if you will solve this particular equation with these initial conditions, from which it implies that r is 1 over gm k square plus c cosine theta minus theta 0. So this is a solution, r as a function of theta. Now, from here, there is an expression gm over ck square. Gm, if you will divide it by c square, you will have 1 here and c here. And this is eccentricity of the curve. So this is basically a general polar coordinates of certain conic section, which is either an ellipse or parabola or hyperbola. Now, it all depends on this particular condition. If it's less than 1, it's ellipse. If it's equal to 1, it's a parabola. And if it's greater than 1, it's a hyperbola. So all these second degree curves are basically solutions, and they are orbits of planets. Planets are on ellipses. That's one of the Kepler's law. You see what we have basically accomplished. We have the Kepler's law here. We have, I wiped it out, but it was something like r squared theta prime is equal to constant, the L. I used letter L. Now what is this? Well, this is actually the angular momentum. So we have a conservation of angular momentum. It's a very important thing. It does not, our Lagrangian does not depend on the theta. It depends, kinetic energy at least, it's not dependent on theta, it depends on theta prime. Now, if it doesn't depend on the angle, it actually results in certain conservation law. We will address this in the future lecture about Noether theorem. So any kind of independence of Lagrangian of some constant results in some kind of a conservation law, which is in this case angular momentum conservation. And Kepler's law and the shape of the orbits based on eccentricity here. So everything was derived. Now what was difficult here, these purely technical manipulation of the system of two Lagrange, Euler-Lagrange equations, I reduced it to one with second derivative of r by time, and then I had expressed the second derivative of r by time with second derivative of 1 over r by theta. So this is basically a little tricky. I'm not the first one who actually came up with this particular trick. Anyway, it works, and if you know this thing, how to, but you see, the most important thing is to basically construct the differential equations which deliver you the solution. And in this particular case, we have derived these differential equations, Euler-Lagrange equations, relatively easily. We expressed kinetic energy, potential energy, and just took a few derivatives, no big deal. To solve it, well, required a little trick, but that's something which is mathematicians are doing quite well. Let's not worry about this. To create the differential equation is the most important part of this, because it can be solved no matter what, even using numerical methodology. So everything is solvable in some way or another. But to come up with this, that was very, very important. And as you see, this approach, which is basically typical for Lagrangian mechanics, allows you to do certain things much easier, like Kepler's law, for example, and other things. The conservation of the angular momentum, shape of the trajectory, etc. Okay, now I do suggest you to read the written material for this lecture. All lectures on Physics Plus and on Unizor.com in general are basically, they have two parts. They have visual part, which is presentation, my video presentation, and there is a textual part. On every page you have the moving picture, and you have a text. And the text is basically more or less the same, except if I make a mistake, for instance, here, I definitely know that the text is correct. So even for this particular purpose, I do suggest you to read the text. Certain calculations are made in the textual part more detailed than here, because I'm kind of restricted with the timing here. It's a lecture, so it should be like about 30-40 minutes. That's it. Again, as I was saying, the website is totally free. No advertisement, no sign-in, no subscription, just use it. That's it. Thank you very much, and good luck.